Good morning, everybody, and welcome to the JKMRC Friday Morning Seminar Series. On behalf of the University of Queensland and the Sustainable Minerals Institute, we'd like to acknowledge the Turrbal and Yagara people as the traditional owners and custodians of the lands on which we meet today. We pay our respects to their ancestors and their descendants who continue cultural and spiritual connection with country, and we recognise their valuable contribution to Australian and global society. My great pleasure today to introduce Leonardo Salazar as our speaker. Leo is a geologist and product specialist at Thermo Fisher Scientific, and he's been working on automated mineralogy solutions since 2007 and Xray micro CT technologies since 2014. He's passionate about making digital rock analysis solutions accessible to everyone in both academia and industry. Leo is involved in multiple projects across the globe promoting high-resolution technologies for geological applications, for providing training, and is deeply involved in R&D activities for SEM-EDS. Please join me in welcoming Leonardo Salazar.
Okay, thank you so much for inviting me today. It's a real pleasure to be here with you guys. And today, I will be talking about some of the new developments that we've been doing on automated mineralogy. Of course, like we have been working in this space for more than, I'm personally been since 2007, but with Thermo Fisher and technology with Quantifying and MLA, there is a long tradition and history on automated mineralogy back to the 70s or 80s. The university heavily involved with MLA, but also we had QuamScan with Intellection back in 2007, 2008. Then with FEI, then we started working on a new generation of automated mineralogy solutions, trying to overcome some of the limitations or some of the things that we were gathering from all users. And then it's been a while since we started working on a new platform. It takes a little of time to develop new things. We went all the way to the basis and started a new platform, and that's what we have today. It's called Mass Mineralogy. So I would like to share this with you guys. Of course, when we talk about automated mineralogy, or in general, rock, analysis, or we are always looking to capture three components. We are always interested on of course, the mineralogy of our rocks, which is very important and controls a lot of the processes. But also, we want to do it quantitatively, of course. And we are also interested on particular, elements or metals that are contained within those minerals. So always we're talking about, it's funny because when I've been presenting on, the critical minerals conferences, and a lot of people mention that, the critical minerals are cobalt, nickel, lithium. Well, those are the metals within the minerals, right? That we are interested in. But we are always interested in those elements and in which minerals they are present, how much we have of them, and basically we are always interested on the elemental makeup of our minerals. There are different techniques that we could use, of course. There are fantastic techniques like ICP, MS, optical emission, spectroscopy. We have XRF, we have LIBS. There is all these different techniques that would allow us to get the elemental quantification. There are other techniques that allow us to do the mineralogy, like XRD, for example. And the texture. Typically, when we talk about the texture, we're talking about things, for example, like what is the grain size of our minerals? What is the association of those minerals? So we typically use like imaging techniques when we capture the texture of a rock. Could be from optical petrography or scan electron microscopy. But the idea of automated mineralogy is to combine those three aspects on a single acquisition, a single data set, where all the information is coherent. Everything is acquired on exactly the same sample, exactly the same surface at the same time. And that's what it makes automated mineralogy quite unique. And of course, we're always looking to improve all the three aspects, especially on the quantification side of things, like the mineralogy, elemental quantification, but also to be able to quantify those textural characteristics. There you are. But today, I'm going to be focusing on, you can use automated mineralogy using different techniques. There are different techniques available right now. I'm going to be focusing on the SEM, kind of the traditional SEM automated mineralogy use of, for automated mineralogy. So this is how it looks like. I can talk about for hours about SEM technologies, but I'm not going to do that today. I would like to focus on our applications and show you some examples. For example, when it comes to mass mineralogy, we always have the SEM is coupled with the software. Basically, the software is the one that automates the whole process, the whole workflow. There are some touch points, and as we have like user interfaces, there are some touch points where people can do input. You have your input into, for example, the acquisition, which is done in maps. You can select, for example, the acquisition settings, and there is a whole bunch of automation in terms of the stitching of the tiles and creating a very large image out of individual field of view. Because that's one of the things when we're working with scanning electron microscopes is every time we increase the magnification, we want higher resolution images, but also the area that we are analyzing, it gets smaller every time. And of course, we want to make sure that the results are representative. That's one of the main goals, right? That's why if we are analyzing particles, we want to analyze thousands of particles or hundreds of thousands of particles to make sure it's statistically robust and is representative of the sample. Or if you have a thin section, you might want to capture the whole thin section to capture the heterogeneity of the rock. So that's why we have in our acquisition, in the acquisition software, you can set up all the automation, acquiring all the individual fields to cover very large areas, but also do it at high resolution. And then at the end of the acquisition, the data is processed and is analyzed. All the X-ray information gets analyzed. I'm going to touch base on that later on, using a library. So we're going to be doing a spectrum matching across with the library. And then the software will give you all the information about what are the minerals in the sample and what is the proportion of the minerals and the quantification, elemental quantification. And then the reporting is probably what we are most used with MLA and QuamScan. Get, for example, like a liberation report or a grain size or a particle size. What we say is like maps mineralogy is not a whole new approach. It's not a new technology. It's basically the evolution of what we had in the past with QuamScan and MLA. And that's kind of the objective when we started this project is to, instead of having two products that are very similar and serving on a very, very similar type of applications, the idea was to take the best of each of them. So there are great, intellectual property on MLA, both MLA and QuamScan. So we wanted to take advantage of that and then take opportunity to create new IP. For example, we have more than 13, 14 new patents associated with mass mineralogy. But a lot of the things that we are doing is on the legacy that we had with QuamScan and MLA. These were revolutionary technologies. Mass mineralogy is more the evolution of QuamScan and MLA, it's the continuation of that development and that work. And so we are pretty proud to use them as the backbone, but we are also very excited about some of the new solutions that we're doing. Some of the things that were quite difficult to do with QuamScan and MLA were things, for example, like what happens at the boundaries of multiple minerals or grains, right? A lot of the most interesting things happens on the grain boundaries. And that was a little bit difficult to work with Quantifying and Emily, mainly because of interaction volume. And if you want to do Xray mapping, some of those Xrays are going to be captured from that boundary between more than one phase. Then we have things, for example, like very fine grain type of textures, very complex type of rocks. One of the reasons we started working on a new solution was because back in 2013, 2014, there was a boom in the oil and gas space, especially with shale gas. It was here in Australia, in the US, all around the world. And it was required to have these type of tools for characterization of this type of rocks. They are very fine grained. There is a lot of minerals that are occurring in grains that are smaller than the interaction volume with electron beam, where the X-rays are coming from. And it was quite challenging to work with Emily and Quemscan because of that mixed spectrum aspect. And in these type of rocks and very fine grained textures, it gets kind of amplified due to the nature of our samples. And the third aspect that we really wanted to improve is the fact that minerals form solid solutions. They may have, of course, minerals, they have, a chemical formula and a structure, but they don't have a unique chemistry. So all these elements, they might be present in our minerals in different proportions. Sometimes the most interesting metals are actually impurities in these minerals. So we wanted to incorporate this concept that, and this is what we use always in geology and in geology, is we wanted to make sure that the software understands that we are talking about things that don't have minerals, don't have a unique composition. Solid solutions, you have a continuum in compositions between two and members. We have elements that are replacing each other. You have substitutions that are not a complete solid solution, but, for example, like you can have iron in calcite, but calcite don't form a complete solid solution with siderite. So we wanted to make sure the software understands those aspects and that we can train the software to deal with these, even some of the most complex cases like espionage. So a lot of the one of the key aspects that we have to develop, basically to help on those three challenges that we were facing with Quemscan and Emily, is what we call the Mixel. It's basically the fact that the X-rays, they don't come from a spot, they come from an interaction volume. And in that interaction volume, sometimes the signal is coming from more than one mineral, more than one phase. So for example, if we have the red one, is our spectrum coming from this particular acquisition point. This spectrum is not a fourth mineral, it's basically the combination of the three minerals that we have present in the sample. So what the software will do is it will classify in two steps. It will first identify the minerals that are occurring in our sample. For example, in here we have quartz. In here we have actually ferro and dolomite. So also it's able to understand that we have dolomite anchorite intermediate composition and classify it as a single mineral like ferro and dolomite. And we have some clays. And then the software is able to deconvolute this spectrum into the individual components. And in every acquisition point, in every pixel, basically every pixel in the image represents an X-ray spectrum that we colorize. In here, we are overlaying the BSE with our mineral maps. But then the software quantifies the proportion of each of the minerals in each of the acquisition points, which are represented in the image by our pixels. So we have here and the software side. Actually, in this red spectrum is 60% quartz, 30% smectite, and 10% dolomite, for example. And then maybe the next acquisition point, maybe it's a 50-50 quartz with dolomite, and the next one is 80-20, and so on. And it will give us not only very accurate results, but also it makes the solution very easy to use, which is one of the aspects that we always wanted to improve, coming from a QuantScan and MLA. The other thing is, when we're dealing with rocks, of course, we mentioned this before, rocks, of course, are heterogeneous. So we wanted to capture a very large area, but we also wanted to cover our sample at high resolution, depending on the texture. For example, this is an example of the shale in the US. And basically, the whole acquisition was done, let's say, with a BSE of around 100 nanometers and EDS 1 or 2 microns per pixel. So basically, you can cover very large areas with at high resolution, and some of these images could have even like hundreds of thousands or millions or even billions of pixels in the image. So basically, what we're doing now is we are taking a little bit kind of the concept of like a Google Earth, in the fact that all the images are stored as a pyramid. So the software doesn't load everything into memory, but it actually loads whatever image you are visualizing at one given time on your monitor. Then when you zoom out, it loads a downsample version of the image. When you zoom out, and when you zoom in, it gives you the full resolution of the image. So that we can visualize very large acquisitions in regular computers. Of course, to classify them, it requires more powerful computing systems. So that's why a lot of people say, like, yeah, this is great. And what is the downside? Well, there are two that we are very open about them. One is because we can cover very large areas. We don't have any limits into how many pixels the images could have, or what is the resolution that you can achieve. Basically, the limit is the specifications of the scanning electron microscope, which is less than 1 nanometer in most cases. And on the EDS, we don't have any limit in how many X-ray points can be acquired. So then the two limitations that we have is basically large file sizes and the fact that you're acquiring for longer periods of time. So you can make acquisitions very fast, or as fast as you like, but you can make them very, 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 very long. So, but that's kind of a good thing, in my point of view. Like the computing, and also the classification, it takes longer to classify, to identify the minerals. And that's the reason we are working on a lot of automation to basically go through the entire workflow in a more automated fashion. So even though the classification takes longer and we are dealing with larger file sizes, most of the process happens unattended, and more of the things happens in parallel compared to like more in a sequence. That's what we used to do in the past. Yeah, but large file sizes are a reality. I remember like 15, 16 years ago, the problem was not enough data. Now we have to deal with too much data and how to make sense of that data. And that's one of the things that we are heavily invested into in Thermo Fisher, with not only with solutions like mass mineralogy, but other solutions for like data management as well, because that's a common challenge that we are facing these days, is how to interact and how to interrogate large amounts of data. And when we come to like imaging data, of course, very large file sizes. When in terms of the acquisition, basically we wanted to kind of be able to like load the samples into the SEM. So typically the samples are prepared in a as a polished section, like always. Very similar to Chemscan and MLA. We have done some experiments in the past, or like more recently. We are our colleagues in China and here in Australia, like Justin Freeman, that we've been looking into, can we do this on uncoated samples? Can we do this on unpolished samples? Can we do this? Can we do 3D mineralogy on, for example, like dual beam systems, like FIPSEM systems, that we could do EDS, in certain parts of the volume, while we kind of mill and capture the 3D images of our samples. Yes, we have done all of that. It's still the most common and popular way to prepare the samples are polished sections. Mass memory works a lot better compared to Chemscan and MLA in the other scenarios. When you don't have polished samples or we don't have coated samples, you can run in low vacuum, or you can run in low vacuum in dual beam systems for 3D imaging. All of that is possible, but still the most common case is to mount the samples in epoxy, give them a polished, and then carbon coat them. Then the sample, the system comes with 2 sample holders depending on the size of the blocks. So if they are prepared as 30 millimeter diameter blocks, you can fit 10 of them. This is for the APRO. SEM, if they are preparing 25 millimeter diameter, you can fit 16 of them. But the idea is not, we don't use the holder as a way to basically know where the sample is in the chamber. In the SEM, that's why we have like a navigation camera. We can take a picture inside the chamber to basically know where the samples are. If we have the time, we'll have a quick recording at the end. But we do use the sample holders to automate the process. So basically, when you load the samples, you can save all your parameters in your template, in a template, when you can just load the template for all samples at once, and the system just run them all unattended using that input that you gave. But of course, the idea is to make a user interface when you don't have to navigate through different multiple interfaces, or you have to do like create a holder here, load them in a different software, put it in the SEM. The idea is to simplify all of that to make a lot more modern software. So the idea is to, if you have a template that you like, basically you load the template. You can, if you go, you can go to file, also load the template to all the positions that you have. Basically, then select the acquisition parameters. If you want to do your tile set or mosaic in a grid, you can do it like a rectangular one or a circular one or a freehand. Any area can be done. And then basically all the parameters basically are saved on these tabs, which can be saved in the template. For if you have repetitive jobs or you want to kind of keep consistency on the acquisition side of things. And that's it. And just play run. I pressed the wrong button. And that's it. And please run. If you load them all at once, then you can just do all the setup with 2 clicks, basically. I have a recording that shows you a little bit better than that. Then when the acquisition is finished, the stitching is done automatically. And then using like a feature recognition algorithm. For example, I remember working with, with MLA. Sometimes when we have our images, you can clearly see the edges of the fields. Sometimes you have repeated particles, sometimes you have gaps, and then that put a lot of strain into the stages. So the stages always need to be like recalibrated and with very precise movements. But these are all mechanical stages that we have on the SEM. Of course, there are piezo stages as well, but they are way more expensive. But the idea is, instead of having a more expensive hardware solution, the idea is to use the software in a smart way to basically solve a challenge that we had. For example, like make sure the stitching is perfect every time. the software can understand what are the features that are repeated in that overlapping region to make that call. And sometimes, or most of the time, it will do it much faster and better than humans we can do. So the idea is to utilize kind of the technology for those tedious tasks. Then after the staging is done automatically by the software, then the acquisition is triggered. The data is actually transferred to a different computer, and then the classification is triggered. At the same time, the second sample is running. So things basically run in parallel on the different computers that come with the system. And then this is the interface that then after the acquisition is done and the minerals are identified, then you can overlay the different images in the software to do some QA/QC. You can have a look at the spectrum, you can have a look at the results. But I'm just gonna show a little bit how different it is from what are some of the differences that we have with QuamScan or MLA. And a lot of that comes into how the system identifies the minerals. Of course, we have a lot more automation on the acquisition side, but also how we are identifying the minerals is a little bit different. So, of course, we all know this. So, X-rays, basically, they are generated from the interaction of the electron beam with the sample. And then when we got electrons from inner orbitals that are getting kicked out by the incoming electrons from the beam, some electrons from higher orbitals replace them and then generate photons in the form of X-rays. And then we just basically count or plot those X-ray photons in a pulse processor that will give us the energy, basically measures the energy of those photons against the number of counts that we get, and then we get the X-ray spectrum. Basically, this is how energy dispersive X-ray spectroscopy works in a nutshell. Is very similar to XRF. Basically, EDS is a form of X-ray fluorescence. The only difference between the EDS that we use on the scanning electron microscopes and XRF is the source. Instead of using an X-ray source, basically in this case, we are using an electron beam to excite those X-rays from our sample. But this is like a textbook spectrum, right? If you look at the previous image, we want to capture hundreds of thousands, millions, or billions of acquisition points. And each of those points is basically a spectrum. It's a spectrum for each acquisition point. So if you want a spectrum, if you want to work with a spectrum like this, then you will be acquiring for months, which is not practical in reality when you want to cover very large areas. So we also want to be able to quantify our elements. That's the main objective, right? To be able to quantify our minerals, but also to quantify those minerals or the elements that are make up our minerals. So now we can directly quantify from our EDS analysis all the elements that are in green. Basically, what we do is we can do a quantitative analysis using EDS. We are using some new techniques for to actually measure that from the X-ray spectrum. We are using, of course, we do a soft correction, remove the background. We are using a standard-based quantification, and we use a top hat to quantify them based on that X-ray spectrum, which give us very good results for the elements that are in green. The ones that are in yellow are inferred. Basically, what we do, the software will do a spectrum matching first. For example, if we have like spodumene, the software can use the whole spectrum of spodumene as a fingerprint of the mineral to identify the mineral first. And then we know spodumene could contain, 3 or 3.5% of lithium. And then the software will renormalize all the quantified results with the ones that are inferred basically after identifying the mineral, which are the ones in yellow. But this is the reality. This is a single acquisition point. Even though we try to aim to get at least 2,000 counts. In this case, we're getting like more like 3.5, almost 4,000 counts. And this is how the X-ray spectrum actually looks in reality. The previous one is more like textbook, right? Very easy to work with the first one, but this is how a single X-ray point looks like, because we want to do so many of them across our sample to create these images. We want to do it fast. We want to do it as fast as possible, but there are some limits in the hardware on how fast can we acquire. Of course, both processors, they get better every time, so we can keep pushing the speed of the acquisition. But at one point, we have to deal with X-ray spectrum. But this spectrum is good enough to basically identify more qualitatively what are the elements present in that acquisition point. In this case, we have nickel, iron, sulfur. And we can map those elements using a relative concentration method, which is more like a kind of semi-quantitative technique. We don't call it quantification because it's the amount of noise in the spectrum. It has a big error margin. So it's more like a semi-quantitative, or we call it a relative concentration method. To basically, we can use this to map where our elements are present independently of the mineral identification. And then what the software will do, this is quite similar to MLA. It will take that spectrum and then it will compare against a database. Here's where kind of some of the differences happen. This database, you can acquire standards and input that into the database, but also the software can predict how the X-ray spectrum for any given chemistry will look like. Also the software comes with a library of more than 4,500 minerals. But also we added, this is something that we added that was based in QuemScan, that we call that we can create the spectrum synthetically based on the weight percents of our minerals. So if you have, for example, information about the weight percentage of each of the elements within the mineral, the software can recreate the spectrum. Or if you have a chemical formula, then the spectrum can be generated synthetically. And it basically opens the door to not only acquire the standards in the cases that you truly need them, but also like you can work with the software offline a lot more. So basically you can keep the system busy acquiring images and data and then process the results offline in your office. So we can generate this spectrum synthetically because the software contains elementary standards built in. And this is kind of, those elementary standards were acquired at 15, 20, and 25 kiloelectron volts. So you can have all this, the big library in one go, created synthetically from composition, as long as you use one of those three accelerating voltages, 15, 20, or 25 kV. Just because those are the voltages that were used to acquire the elementary standards that are used in the software to create that spectrum synthetically. The other cool thing of this is when you apply, for example, like a substitution rule, you say, I don't know, in this particular mineral, iron can be replaced by magnesium, for example. Then the software can recreate the spectrum also synthetically when you have different ratios of magnesium and iron in the sample. And also, it's not only the magnesium and iron that, when they replace each other, the other elements, the whole spectrum actually, it will look different. If you have like silicon or oxygen or the other elements, the whole spectrum is going to look different. The ratio of the peaks is going to change. And the software can predict how the spectrum is going to look like. The same when you have solid solutions, the spectrum can predict how intermediate compositions or how the spectrum of intermediate compositions will look like based on the end members. So this is what I have a quick example. And this is basically how we classify minerals, right? We basically take the end members and intermediate composition, or intermediate varieties. Basically, they could be classified as the ratio of those end members. A very easy example is our feldspars. For example, you have like a labradorite or andesite. They can be identified by the proportion of albite anorthite. And then we wanted to incorporate this in the software in the sense that this is how we classify minerals, and the software should be able to understand that. So we did a quick experiment. This is a while ago. This was like, I don't know, like 2017 or earlier, when we were saying, okay, let's test this. And we did it for a whole bunch of different solid solutions. But for example, if we acquired a standard, for example, like labradorite. So we took a measured labradorite from a mineral standard with known chemistry. And basically we say, okay, how good is the software to predict how the complete spectrum of labradorite will look like using the albite anorthite ratios? Basically, the one that is the interpolated, the one predicted by the software, is the light blue. And the measured one from a standard is the red one. And they look almost identical. So this is what gave us excited, that it takes the product from a more like an R&D project into something that we say, okay, we can apply this to not only like shale in the oil and gas industry, but we can apply it to every single type of rock. We have tools that it will make resolving, for example, mixed spectrum cases, solid solutions, elemental replacements, a lot more easier than we have in the past. And that's why we made the decision to commercialize the technology. So we have a lot of companies and universities, research institutes working with us. So we are very grateful for the input and giving us the chance to develop together this new solution. So then when after the spectrum gets compared against the database, the software will find the best match. But you can imagine if you have 4,500 minerals, trying to find the best match could be very time consuming. And also the software will be deconvoluted mixed spectrum cases. That will be super time consuming and still might leave the door open to false positives cases when you have, when you have a very big, library and you want to match against very like 4,500 minerals, it doesn't guarantee the results are going to be more accurate. So what we recommend is to have a short list of maybe 50, 40, 60, 100 minerals that you're interested in for a particular deposit, for a particular type of rock, for a particular application, and constrain the list to those ones. And that's the way you can also train the software to say, okay, these are the ones that make sense for this type of rock. And then the software is going to find the best match, in this case with pentlandite. So the red one, so the red spectrum is the one that is identified. So I give you spectrum matching. It's around 95% spectrum matching, so quite high confidence. And it gives you basically the result. And it will do it for every single acquisition point. So a little bit similar to emulate, but we give a lot more flexibility into that spectrum matching. So once we have this, once we have our minerals identified, the next point is to be able to quantify, do the elemental quantification. So what the software will do is it will take every single spectra that was identified as pentlandite in this example as the same mineral and create a sum spectrum or a super spectrum. With this super spectrum or sum spectrum, instead of working with 2,000 or 3,000 counts, we have more like 1 million counts or 100, tens of millions of counts or even hundreds of millions of counts, which makes the noise basically disappear. And this is a lot more suitable for doing quantitative work. The other thing, you can use different throughput. For example, like this is with the 600, but you can also use the other ones like 90 kilocalories per second if you want higher spectrum resolution as well. It will work for all of them. You don't need to do anything. The software will understand that you are working with a particular throughput, and it will do that. And based on this, some spectrum, it will remove the background. It will do the quantification using the standard-based quantification and using the top hat to give you the results. And these are the results that will be used later on for the rest of the reports. Basically, the reports are just an interrogation of a database. Good thing, when we're talking, academia or research institutes, all the information is safe on an SQL database. So most universities, they are more keen into develop their own or basically interrogate the data themselves. So you can go into the SQL database directly. It's open source. So you can just go and interrogate using your own scripting skills. So you don't need to go into our interface if you don't wish to. We don't want to kind of log anybody with proprietary formats. But these results are the ones that are used for the reports, basically like the assay, the performance. In this case, we have the nickel. 84% of the nickel is in pentlandite. And of course, when we talk about the texture, we are, of course, dealing with a scanning electron microscope. So the idea is to fully utilize the capabilities of the SEM. So at the same time that it's doing our EDS at a different pixels, at a different spacing compared to the BSC imaging, then we can have much higher BSC images with the resolution that you specified with decoupled EDS. So it happens simultaneously on the same field, on the same acquisition, but the X-ray spacing could be quite different compared to the BSC imaging. So for example, you can have a BSC image of 50 nanometers or 30 or hundreds of nanometers or even microns. And the EDS, you can pick and choose whatever is the most suitable, take into account the features that you want to resolve, and take into account as well the time that you have available, of course. So you want to go to very large areas, you can do an X-ray spacing very coarse, and then get information very quickly, but also at lower resolution. So the two, the BSC and the EDS, are decoupled when we do this X-ray mapping. And this is, we present the images. For example, you can present them in a heat map, very similar to like microprobe type of visualization, when you can select a particular element and visualize it as a heat map. This is using the relative concentration method when you visualize them. So the areas in blue are the ones with the low concentration. The areas in red are higher concentration. We're working with quite a few researchers actually in UQ. They are incorporated some of these images. Some of them might look a little bit familiar. Basically, so we wanted to do the element distribution map independently from the mineral identification. So even though you say, I'm still working on my mineral list, then you can say, I'm interested in a particular, I'm interested in iron or titanium, then you can visualize those elements independently from the minerals, in the same data set, in the same image, in the same interface. So we have titanium distribution as a heat map. And another case that it was particularly difficult in the past, and this is actually more, becoming increasingly more important and critical, is, for example, working with minerals containing rare earth elements. Rare earths, doing EDS on rare earths, especially large area mapping, it was a little bit challenging because of this, basically. If you acquire, let's say, 2,000 or 2,500 counts, the X-ray spectrum is very, very noisy. I see one worse, for example, in QuemScan, that we only acquired 1,000 counts. It's just, sometimes you say, no, this is just noise. I cannot make any sense of, the spectrum. But it's still good enough to identify the mineral Of course, the spectrum matching will be a little bit lower. But then what we recommend doing, and this by the way, this is the visualization. We have the BSC image overlaid with not only monazite, but also basnasite in this particular case. This is an example from China, thanks to the Chinese Academy of Sciences. But then what we do is you can tell the software that every time you acquire or during the acquisition, every time it encounters a mineral like monazite, instead of acquiring for a fixed amount of time that gives you roughly 2,000 or 3,000 counts, you can tell the software acquire 20,000 counts or 10,000 counts only on those minerals that I am interested in, that, for example, contains rare earth elements, because you want to reduce the amount of noise in the spectrum to get more accurate results. And of course, reducing the noise on the spectrum is very useful, because that's what is going to improve your quantification in that mineral. So then in this case, you can easily then, after reducing the amount of noise by acquiring more counts, then the software can also create the sum spectrum. We'll create the sum spectrum for the whole monazite in the sample, the average. But also when you use this long count trigger, it also creates the sum spectrum per grain. So you can also say, okay, what is the composition per monazite grain? That you can also take it into further, or zircons, for example. What is the composition of the zircons for each of the grains? And then you can input that information. For example, when you have like laser ablation ICP-MS, you want to do like isotope analysis, trace element analysis, you can use this information to quantify the major minor elements and let the ICP deal with the trace elements, the isotopes, and the ones that are kind of truly kind of shine kind of the benefits of a system like ICP-MS or like laser ablation ICP-MS, which we're working, by the way, quite recently on that topic. Another topic also from China in the critical minerals space is cobalt. Of course, everybody's chasing cobalt, including not only outside China, but inside China. And we found that this sample, everybody knew this sample contains some amount of cobalt, and some of that cobalt were in pyrite. So yeah, it could happen as an impurity, and the software will understand that. We can, tell the software that. And then, so we did a big area map of, our pyrite. By the way, this is a copper sulfide deposit. That's why you have mostly it's chalcopyrite. So cobalt is a byproduct of the copper sulfide kind of processing. But I was very interested to know where is the cobalt, what are the minerals that contain cobalt, and where it is distributed, how it is distributed. So not only how much cobalt do we have or how much cobalt we have in pyrite, but how it looks like, how it is distributed in the sample or in our brains. So then we can zoom in into some of these areas with pyrite grains. In this case, again, we have the BSC image. We love this kind of the visualization. We have the BSC image in the background overlaid with our minerals. We have chalcopyrite, pyrite, and carbonates. And then everything is still be classified as pyrite, especially because this cobalt in this case happens as an impurity, with the highest concentration was probably like 2%. So the spectrum is still very, very similar to the pure pyrite spectrum. But then we say, okay, let's see how the cobalt is distributed in the pyrite. So this is the cobalt distribution map. And the interesting thing is, cobalt is not homogeneously distributed in the sample. In some other samples, was the opposite. It was more concentrated in the core of the grains compared to the rims, but also some these very, very nice sonations. And it was not present in every single pyrite. It was present in some pyrite. So this gives some of the researchers some clues into, okay, maybe those kind of the conditions or how the spirals, the formation of the pyrites, how they form, that makes the cobalt be distributed in a particular way. We can zoom in. So, and the next question is, what is the concentration of cobalt in pyrite in particular areas that we can detect? Anyway, we're talking about EDS. EDS is not particularly known for trace element analysis. It's more like for like minor and major elements. So, so we check, and then the areas with higher cobalt in this example, they had around 1.8%. And then we can still identify cobalt and quantify it as low as around 0.3%. A lot of people will be, a very common question I will get asked is, what is the lowest concentration you can detect? And the answer is, well, it depends, right? It depends. We are talking about, in this case, we're talking about like cobalt in pyrite. We're talking about the areas that contains the lowest concentration of cobalt within pyrite in a particular X-ray point. Yeah, the lowest concentration was 0.3%. Typically, a lot of people say like 0.1% is kind of the rule of thumb, but in reality, it depends on where is the element, in which mineral it happens. For example, in the case of cobalt, the cobalt peak is actually very next to the K beta peak of iron. So if you are interested in particularly cobalt in pyrite, then the detection limit for cobalt is going to be a little bit higher than if you have pure cobalt or pure element, metal. So the same happens for all the elements, depending on what accelerating voltage you use, depends on in which mineral they are analyzing. So there is not a straight answer to that, but in this case, it was around 0.3, 0.4%. And of course, everything goes into the software, and then this is kind of how it looks, kind of that sense of familiarity with our discover of MLA, that we can report multiple samples, compare, combine samples. For example, if they were split into multiple size fractions, you can input that weight percent or the weight distribution for the size fractions, combine them into the original sample before splitting. Then you can run different scenarios by doing like, for example, applying filters that you can filter particles based on proportions of the minerals or the elements or particle size or grain size, for example. Then you can generate reports like a liberation reports, grain size, the deportment reports. So all of that is kind of what we all know automated mineralogy to be known for. We just kind of fundamentally, we are improving the way that we identify the minerals. We are making it more accessible, more user-friendly, and also improving the automation aspect. For example, this is an example of the locking report. This is the same as in MLA. This is basically a particle classification exercise. When you put in one bucket, you put all the liberated particles. When you have, I don't know, 80% of, for example, pyrite greater than 90%, you just put them in that bucket. And then you have the binary categories, ternary complex categories, and the software will give you a breakdown into what are those associations with the minerals that we are interested in. We don't have much time left, but I always like to show you a quick kind of demonstration into how it is. This is an Apple system. The samples were loaded in the holder. The navigation camera was taken. You run a very quick alignments. You can select the areas that you want to acquire. You can put them in whatever order or orientation you like. You can use the holder to automate the whole acquisition. You can take surveys like MLA and then select particular areas, even using the freehand, which is quite fun. And you can specify particular areas or a center or a feature that you want to capture, and then select the elements that you want to map. Apply, for example, like background filters that you don't want to acquire X-rays on the epoxy, and then the system is just running by itself. And then all those settings can be saved in the software next time, for next time. So the next time you need to do is to call that template and apply that template. And then the software, you just acquire everything. Of course, I speed up this because, yeah, we didn't have enough time left. This is about 30 minutes acquisition, condensed in less than 2 minutes. Then everything, if you notice, there is an overlapping region. So that overlapping region is what the software will use for stitching. I showed you there before and after stitching. All the fields are moved. Everything now gets classified in the support computer. And then you have all the classification, including the mixed spectrum cases like pyrite and quartz. In that case, you have element distribution maps. You can present them as the heat maps. And you go into the quantification aspect using the sum spectrum. And then when you're ready, just go into the reports. So this is basically like 2-minute condensed video that I have to show you. And I just want to leave you with some beautiful images of also cathololuminescence. There has been recently almost like a renaissance of cathololuminescence. It used to be quite popular in the 90s, but the problem was it was a little bit difficult to use. Sometimes you had to use parabolic mirrors, which kind of makes the use a little bit more restricted. You have to work with very short working distances. You cannot cover very large areas. But now there are some CL detectors. In particular, this one is developed for our microscopes and is 100% compatible with maps, with the microscopes, and allows you to acquire CL images with the same working distance and at the same time, along with the BSC, with the backscatter electron images, with the secondary electron images, with the X-rays, and CL can be acquired, all of them at once in a single acquisition. And it's compatible with maps, doing large area tile sets or mosaics, something that in the past was not possible. And it's becoming like, there is almost like a renaissance of CL that everybody loves, especially because it is an example of zircons. It shows these beautiful images with zonations where it gives you confidence on where you can acquire, for example, like spots for, let's say, laser ablation or doing isotope analysis, or exactly where to acquire and get the most accurate and most statistically valuable results. So this is what I have to show you today. Feel free to reach out anytime. I'm more than happy to have a chat. I don't know, do we have still time for questions? Yeah.
Leo, that was fascinating. We do have some time for some quick questions. We've got someone online has raised their hand, which is a rare occurrence. So, Abes, you are currently muted. If you would like to ask your question, please go ahead. All right, well, while I'm waiting for Abes, we'll just go to another question here from Enrique.
Hi, Leonardo. Is on? Okay. Hi, Leonardo. Thank you for the talk. Really interesting. I just have like 3 questions. Regarding, do you think it's necessary to still like do a mineralogical validation with other analysis? Especially like because like, you know, traditionally like automated mineralogy is validated with XRD, I don't know, like historically. Also, in the case of the cobalt and the iron peaks, like the differentiation on the EDS, is it like, are you like working with like the another electron energy levels just to differentiate like those elements? And also, with which commercial laboratories are you working in Australia?
Okay. So to answer the first question, yes, we highly encourage to use other analytical techniques. We are doing characterization work. One technique, for example, automated, and that's kind of the trouble sometimes, like say, like, yeah, with automated mineralogy, we don't need to do anything else. Well, not quite. I think is when you have multiple techniques and you get when the when these different techniques basically get to an agreement, that's what it gives you the confidence on the results. So we always encourage to, of course, you keep using your XRD, keep using your XRF, but we're seeing a trend a little bit more into using analytical techniques that complement some of the limitations that we have with automated mineralogy. For example, like isotope analysis, trace element analysis. So it's becoming now is very popular. It's becoming very popular, or it's been around, for a while. We are working maybe to improve that workflow is with combining automated mineralogy with laser ablation ICP-MS. That will give you that kind of additional information that you might not get from purely EDS. But of course, it's always a good idea to do a correlation with XRF or a correlation with XRD. And that because that's what it gives confidence into the results. And also in cases that you have ambiguous answers, sometimes we are talking about EDS is a purely chemical analysis technique. So it's not going to give you information about polymorphs. So you want to kind of resolve those polymorphs, then it's a good idea to use, for example, things like XRD or Raman spectroscopy as well. It's another very popular for those type of cases when you have like polymorphs of the same, yeah. The second question, to differentiate, for example, like the cobalt in pyrite, because it's very close to the K beta peak of iron, we're looking at the entire spectrum. So what happens is, even though when the cobalt concentration is very low in pyrite, you don't see a discrete peak. But then what happens is the spectrum is, I don't know, we don't have a whiteboard, but then what happens is the spectrum in that particular energies, the peak of the ion, the K beta peak of the ion is not symmetrical. Basically has like a shoulder. So then the software interprets that shoulder and it will deconvolute that from the ion peak to actually identify the cobalt. So it's more like, it's still directly from the spectrum, but it's basically, it's not seeing that peak, but it's seeing like there's an asymmetrical peak of ion, and then it will interpret that into that is cobalt present in the sample. And the third one, yes, there are commercial labs available in Australia, in Brisbane as well, like ALS. They have, we are very grateful, we're working with them. But we're also talking with other service labs, of course, in Australia and around the world.
And my apologies to the online questions. So that is all we have time for today, but please feel free to reach out to Leo with your questions afterwards. I'll ask you all to join me in thanking Leo for his presentation today. Next week, we have Ian Satchwell talking about developing infrastructure and supply chains in remote areas, looking at specifically the Pilbara region, using lessons learned from remote northern Canada. I hope you can all join us next week for that.